Hey everybody, it's been a while. So here's just a little taste of what's coming. This is a quick one. Have a good one, everyone.
Okay, you need to create a negative potential. You just need to create a negative, right? Because if you make a negative, the positive ions will go to it. If you're really simplifying it, you say, okay, well, just do the Thomas Townsend Brown effect, TT Brown, right, guys? Asymmetric capacitors, same idea. Asymmetric capacitors. Our asymmetric capacitor causes lift. This is the same idea as one side is negatively charged, so the positively charged side is lifting towards the negatively charged side. We're using that same concept, and now we're saying instead, make it happen in the middle. Okay, you would say, okay, well, build an asymmetric capacitor, but instead make it radial and make it towards the middle with the negative point.
Take the secondary on the bifilar wound coil is going to this light right here, which is 4 panels of 94 volts to light each LED panel. It's going to be pulsed with 28 volts from a function generator at 428 hertz, 20% duty cycle, through a horizontal deflection transistor, and then to the coil itself. We'll show you the output, but this is a means to an end, ladies and gentlemen. I'm going somewhere with this, so pay attention. The next few videos in this video series will kind of show you where I'm headed. Alright, so we're going to turn this on in 3, 2, 1. As you can see, the light is, well, almost blindingly bright.
Chat. You're looking at field reverse configuration. The magnetic mirror setup, this was the precursors to FRC.
If we were to cut our sphere in half and visualize excitation with color, then this behavior would look like a drumhead. However, this kind of radial behavior is only found in acoustic spherical harmonics, or within a physical medium. This wave oscillates between higher and lower pressure as the particulates of the medium compress against and expand away from each other.
The magnetic field will contain the electron because the electrons don't weigh anything. The ions are much heavier than the electrons, so they will not contain the ions, but it will contain the electrons. Boom.
Alright, so what you're seeing here is a thermal imaging picture of the coil in operation at 1 kilohertz. You're seeing the temperature of the ambient temperature of the room and the coil itself. And as it progresses, the temperature in the room starts to shift, and so does the temperature in the inner part of the open core of the coil itself. So this picture that we're seeing now is the ambient temperature of the room is at 24.5 degrees Celsius. The coil in operations at 43.5 degrees Celsius. And the inner part of the open core is at 19.6 degrees Celsius, which is almost a 5-degree Celsius difference between the ambient and the inner open core. And that is something that needs to be investigated. So, what you're seeing at this point, from my understanding, from what I've been shown and what I've been taught, that this is a non-equilibrium state of a coil in operation. And this video is a series of clips attempting to explain that. Thank you very much for your time.
Because the temperature's there, like how that part of the plasma is uniform temperature, perfectly exactly the same. In an equilibrium plasma, you should not see any heat signatures like that. In an equilibrium plasma, it should all be the same temperature. In a non-equilibrium plasma, you can start to see shapes of temperature like that. Okay.